Welcome, everybody, to my favorite lecture of the semester. So let's do a quick recap of what we saw last week, and then we'll jump right into Booleans. So the most important piece of information that I gave you is that this is a database lecture, technically, and we have data shapes, tables, the most popular ones, thousands of years old, trees, graphs, cubes, and vectors, which technically are the new way of handling unstructured data like text, audio, video, and so on. And of course, the focus of this lecture is precisely text. So we are going to see a lot of vectors, a lot of matrices, a lot of linear algebra, with all sorts of things that we'll put in the matrices, as we'll see during the semester. But of course, not only, it's going to be a bit beyond that. But you'll see that it's a nice opportunity to apply all of the knowledge that you have acquired in the linear algebra lectures. So our goal that we actually start today is to find unstructured data that satisfies some information need. I'll give you the exact definition of this and how this is different from a query, from within large collections. We don't just want to retrieve something on small text files. We really want to do it potentially on the entire internet or in an entire very big library, including the contents of the books. So I have a first question for you to help you wake up if this is your first lecture of the day. Starting with this one, do you remember what the Dewey Decimal Classification is? That's something that I told you last week. Is it the core algorithm used by Google to index the web? Is it a number-based system used by many libraries in the world to sort and retrieve their books? Or is it a standard used by mathematicians to classify sets? This classification is also paramount to information retrieval, as documents are encoded as numbers, or query Dewey, and etc. All right, we have a majority. Who used Google to answer this question? That's okay, right? It's allowed. Nobody? You knew it? Who used ChatGPT or any AI? You knew it. Who knew it? Very good. Okay, very, very good. So let me get back to the slides. If I prepared correctly, should take it where we were. All right. So let's start with a naive approach, and I'm going to ask you to think about it. Imagine that you have some text. Let's say I downloaded the entire works of Sir Arthur Conan Doyle, Sherlock Holmes. It's allowed, it's public domain now. So I downloaded all of that, and I have it on my machine, and I want to look for specific words in that text. There is no index at the end with the pages and so on, right? I just want to look for specific words. What would you do? Any idea? Yes? Yes, we would go through the test and to the text and look for words. Are there any specific tools that you would use for that? Anything, any tool that you want, command line tool, IDE, anything. Okay, so you would open it with a text processor like Word or any equivalent, and you would search for it, right? That's fair enough. That does the job. If it's not too big and it fits, okay. Any other ideas? Any other tool, for example, on the command line? You're all computer scientists, right? What do you use in the command line? Yes? grep, yes, exactly. We could use grep. Let's try this. So I actually did it. I downloaded the entire corpus. That's how it starts. 3 megabytes. It's actually not so much, right, in terms of bits, right? Of course, took a whole life to write all of this, but it really fits easily. And it's reasonable to open it in a text processor because 3 megabytes is perfectly within what is possible, right? But let's say we use grep. So now this is my query, and I want to, for example, look for the word lawyer, and I want this match right here. So indeed, I can use grep. Grep lawyer, corpus.txt is the name of the file from which I want to read. And that is going to magically output all of the lines, because there's lines, right? There's carriage return at the end of every line, so there's lines. And if you look carefully in here, you will see on every single line that is returned, there is, as desired, lawyer, here, 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 here. You see, on every line, you will find the word. So that does the trick. We can look up a specific word or sequence of characters in that file. Now, how could I do it with a conjunction with and? I want lawyer and I want Penang with grep. How can I do that? Both on the same lines. I want all of the lines that contain both of them. Absolutely, you can use a pipe like this. So you have the first grep like this, the lawyer, and then you pipe it through another grep command, and you see now we have both words on the same line. So yes, now more complicated. What if I want? So now it's a triple conjunction, and I also want a complement, a not. Maybe you need to know grep a little bit for that, right? Turns out there is a parameter for grep that is -v that reverts the whole thing, and that outputs the line that do not contain, in that case, silver, right? So you can check. The second line here has silver at the end, right? So this one is excluded, and now you get the line that contains the first two words and not the last one. Now we are getting somewhere, right? Because now we are querying words, we are querying conjunctions of words, and not, you could imagine, or as well. So what we already have somehow is a query language, right? It's a Boolean-based query language that allows us to combine words with and, or, not, and build queries. And we also have a very naive implementation of this, where as a human, I can write my grep comments that do this. And maybe you could imagine writing a small, I don't know, a small Python program that takes the query and even outputs the grep command, right? But of course, it would be too easy, right? If that would be it and the lecture is over and now you know how to query documents. There are a few shortcomings with this approach. It's not perfect. There are a few things that we are still missing to get a really usable system. And so I have a question for you on this. Which one of the following, multiple answers allowed, if I did it correctly, is the following shortcoming of grep? First, maybe it cannot rank the results. Second, maybe it sometimes returns documents that do not contain the term being looked up, that do not contain, sorry. It doesn't have proximity semantics, like you cannot search for words that are specifically next to each other, for example, or it cannot scale up so easily. Or maybe it doesn't always return all the matches, not perfect. It might have false negatives, we see that what it's called, or it doesn't support wildcards. So which one of these do you think are shortcomings of grep? Mhm. So the majority is correct. It is true that it cannot rank the results. It's just in the order of the in which it finds them in the file. At least that I know, right? Maybe somebody knows a way, and then that would change the answer. But I don't know of a way. It doesn't have, of course, you could do it using another command line tool. Of course, you could always program it. It doesn't have any proximity semantics. That is true. You can have regular expressions and so on, in fact, but that doesn't tell you queries like next to something or within a specific distance. It cannot scale up. That's true. This is a bit brute force, right? We just launch grep and then it goes through the entire document. You take 10 times the size, it's going to then take 10 times to take 10 times the time, right? So it's a linear complexity, right? So it doesn't scale up so easily. If you give it something huge, that might take a while. If it doesn't even fit on the machine, that's also problematic. And wildcards, well, it supports regular expressions. So that kind of allows you to do that sort of things. Let me go back to the slides. Again, hoping that all of that was prepared correctly. So these are the regular expressions. Who remembers them? Normally you all saw them, right? Theoretical, who saw regular expressions already? All these automata, very good, very good. So this is the sort of expressions you have where you can, this is an or, this is a plus, which is one or more, and so on, all letters from A to Z, and so on. And then we have wildcards that's known as the clean star here that takes in the dot is any character, and that would be a wildcard in that case. But indeed, a shortcoming is that we cannot do it on a very large collection, like something absolutely huge that terabytes might take a while, petabytes, you can forget it. grep is not the solution. In fact, this is exactly why it turned out into a billion-dollar company, I should say trillion-dollar now. But basically, at first, it seemed completely crazy, right? Download the web. We're going to download the entire web and index it to facilitate search, right? But that's not something you just do in a few lines, just like that, right? It takes a lot of time. In that case, years, right? The other thing that is supported in many systems is proximity search. If you want to look for words near each other, like typically in a certain distance, within 2 words, within 3 words, that doesn't handle it. You could argue kind of because it finds them on the same line, right? But that doesn't give you much control over that. And finally, it doesn't rank. It doesn't allow you to say that a specific line might be more relevant to you than another specific line. It just outputs lines, right? In the order in which they are, either they are in the results or they are not in the results. And this is very much unlike this kind of system that allows you a search engine that allows you to rank the most relevant pages, right? With in that case, with the PageRank algorithm that was at the foundation of Google. But we can still do something about it. If we continue to think about how we can improve this, you might have seen at the end of books these alphabetical lists of words, right? And with every word that there is or expression, there is a number of pages on which you can find these words. This allows you to find the words much quicker than if you had to actually read the entire book and search for the words, right? Here you directly land on the pages that contain the words. This is called an index. Of course, they have existed forever, for centuries. You can see them even in old documents, for example, in the documents of birth and deaths and weddings and so on. Typically, at the end, you have indices. There were no computers. It's human beings that actually built them. And so here there is an idea that we can exploit in order to build our system. Because now, if we were able to build something like this that would directly point to the places where we can find these words, then that would actually help. So this is the starting idea. But in order to do that, That's what I tell my master thesis students. Do not rush into the code. Sit back and think about it. Before we write any code or try to build an index like that, we need to abstract a little bit and do some work to simplify things and think of the model with which we are working. An example of model is relational tables. When you have a relational table, then in your model, you have the notion of row or record, you have the notion of column or attributes, and all these things. So we need to think, what do we have here in the context of information retrieval, in the context of searching words somewhere? Well, the first concept that we have is the concept of a document. A document, in modern engines, you see them nicely displayed on the page, right? So every one of these outputs is a document. That's also what you have on Google. But you can also view them in a library as the books. Every book is a document. And so when you enter a search, you're actually supposed to find some documents that matches your search, right? So that is an important concept in the model that we want to build. The name we have for this is first-class citizen in data modeling. A first-class citizen is basically a concept that is core to the model that we are building. And documents are, of course, first-class citizens because this is what we want to look, right? So to look for. So this is the first one. The second first-class citizen in our model is a term. A term is basically whatever you look for, like a lawyer was a term, silver was a term, and so on. And these are also examples of terms. And here you already see that it's actually not as simple as it seems, because you might think, okay, a term is just a word in the dictionary and that's it. Yes, works for a lawyer, Switzerland, maybe if you also have names in there, Sherlock. But look, Unterwalden niet dem Wald, which is the official name of the canton Nidwald, I think. It has spaces in the middle, right? So it's not just as simple as saying it's a word in the dictionary. ETH Zurich, that's the same, has a space in the middle. Watch, run, paper, book, these are all words in the dictionary. So I'm not going to spend too much time on this complexity today. We'll do it next week, where I'll spend the entire lecture showing you that it's complex to actually handle that. For now, I'm just assuming we have something called a term, and we have such dictionaries of terms that list everything we can look for, right? So for now, we don't worry how we actually build that list, but we have terms. So we have terms, and we have documents. Now, let's look at the relationship between documents and terms, right? So I took just a popular example for Switzerland. Let's call it D. That's document D. What do we want to have as a relationship between the document and the terms, right? So we have the documents and the terms. Now we want to link them. We need to think in terms of abstraction. The first thing that we might want to express as a relationship between the two. Oh, by the way, if you don't understand German, that's okay. You don't need to understand German. It's just text, and you just need to see that it's actually good for abstraction if you don't understand Swiss German. So here we can say, for example, that a term is included in a document. For example, the term Hölzli, right here, is included in document D. D is the name of the entire document. So here we have the semantics of set theory, as in a document is a set, and a term may or may not be a member of that set. It may or may not belong to the set. So that's the first way that we could characterize the relationship between terms and documents. Another way could be a bit more involved, not just saying it belongs to it, but also the number of times it occurs in the documents. For example, I might say that not only is Hölzli in the document, it appears twice in this display on screen, right? So I would have a concept of cardinality, right? Hölzli occurs twice in the document. That's the second way that I could connect the terms and the documents. There is a third way. Can you maybe guess it? Let me ask the question differently. Imagine that you don't have the documents. I remove it from the screen. You just have a huge list of the memberships of the terms and the document, or perhaps even with cardinality. Can you reconstruct the original document? Who thinks you can? Who thinks you cannot? Why can you not? What is missing? The order, exactly. We are missing the order. And that gives us the third way that we could do it, which is of ordering the occurrences of the terms, right? So we would say in that case that Flamme comes before, in front of für, right? Before. Now, it's slightly more subtle than that, because in that case, you're just not saying one term occurs before another, you're saying an occurrence of the term occurs before an occurrence or another term, right? But basically what I'm interested in here is the order, right? Now, what are the names of these things? Here I said it, that's called a set, right? Document is a set of terms. What would it be called here? If I have this kind of relationship between the two, it's not a set, it's called? Anybody? Starts with a B. A bag. Have you heard of it? A bag? A bag is the same thing as a set, except that you also have the information on the number of times that something occurs in a bag, which you don't have in a set. In a set, either you're in it or you're not, but there is no cardinality. But in a bag, you might have multiple occurrences. And here, what would it be called? The abstract version of what this is, if we have the order. Let me guide you. It's an abstract data type, just like set, actually. A list, yes, exactly. That is a list. So you see, it sounds very basic, right? But this is important. This work is important. So we have terms and documents, and now we have a way to characterize them as a set. Document is a set of terms, a bag of terms, or a list of terms, right? So concretely, if we have them as lists of terms, then we do have the inclusion, the occurrence, and the order, right? So technically, we can reconstruct the entire document if we took the terms as they appear in the original document. Now, if we have a bag of terms, we drop the order. We forget about the order. So now I end up with this, where I still have the information on the number of occurrences. For example, this Hölzli that appears twice is right here and, here. Right? So you do have the occurrence, but you don't have the order. So of course, that's not fun anymore to read. If you try to read a novel like this as a bag of terms, it's not fun at all, but it's useful if what you want to do is index and retrieve things. And if I now look at it as a set of terms, then this is, I need to operate, yes, this here is going to disappear, and now I have a set of terms. So that's it, and now I deleted the duplicates. Hopefully I didn't miss any, right? So you see, list, bag, set. Remember this is very important, because every week in the semester, we will either abstract as lists, or as bag, or as sets. Every week it's going to be different, and we'll see all three of that during the semester. But it's important because you always need to keep it somewhere in your mind. In every week, are we currently viewing that as a set or as a list or as a bag? Because that impacts the system that we are going to build. Okay. Today, we are going to use sets. No lists, no bags, just sets. I'm just interested in knowing if a term appears or not in a document. So a first way of encoding that, now we want to start implementing, right? So imagine that I want to encode in my system as a structure in memory for each term in documents, whether or not the term belongs to the document. What would such a structure look like? The most naive way to think about it. For every term and document, yes or no, does the term belong to the document? Any ideas? Who sees some sort of two-dimensional grid in here? Right? A huge two-dimensional grid of Booleans. What is it called, a two-dimensional grid? Linear algebra, it's called a? A matrix, exactly, a matrix. So we are going to have a matrix in order to store that. 1 or 0, every time it's a matrix of Boolean. So what we are going to have in this matrix, every row is going to correspond to a term. So now I'm going to index them with a mathematical variable, so I and j. So I is for a term and j is for a document. And at position ij, so row I and column j, I will have a 1, or the Boolean true, if document j contains term I, and a 0 if document j does not contain term I. So this is what I get, right? Of course, in reality, we have many more documents and many more terms, right? But in order to fit on a slide, I just took 10 documents and 6 terms. Who sees here the sets? That every document is a set of terms. Who could give me the sets? Who would be able to give me the sets for every one of the 10 documents? Very good, most of you, right? You just need to look at the columns because every column is a document. So I have here document 1. It has term T and X. I'm abstracting a bit. Of course, these would be words or real life things, but I just gave them some single letters. So document 1 contains T and X. Document 2 contains only V. Document 3 contains T, U, V, and X, and so on, and so on. And you see, as expected, I don't have any information on the number of times it appears in the document. I don't have information on the order in which they appear because we have the set semantics. So I cannot reconstruct the original documents. Document 1, sorry, might be TX, TTT, XX, TX, and so on. I don't know, could be anything, any document that has T's and X's, right? And the same for every document. So the semantics is this one means that document 5 contains term Y. Okay? So you just need some time to let it sink so that you can then easily manipulate it. And now if I want to push a little bit some math, I love math, so I'm trying to preserve you a little bit, but still I can squeeze a few formulas in there. So basically this matrix here can be seen as a function that goes from the Cartesian product of terms and documents. So for every pair term documents, I associate it with a Boolean. Remember this exponent notation, that means it's a function. When you have a function from A to B, that's B to the power of A, right? Who knows this notation? Right? You can either do it this way or with an arrow. You would have terms times documents, arrow, right arrow, B. Let's see. All right. So it's a function that associates pairs of terms and documents to Booleans. So now that we have this, we can start querying. So what does query Y return? Somebody looks for Y. That should be easy, right? Just a bit of mental gymnastics very quickly, but that normally you should answer very quickly. Is it 1, 2, 3, 4, 6, 7, 9, 5, 8, and 10, or nothing, or everything? That should be quick, right? I assume, for most of you. What does query 1 Y return? So which documents? Oh, wow, 100%. That's great. You're following. Awesome. So you get the whole idea. That was 4. I think it's 4. This is where we were. So now remember that we don't just want to look for terms. We also want to be able to execute Boolean queries with and, or, not, and so on. So what if I might need to remove this Zoom. Maybe you don't see it on Zoom, but in the lecture hall, there is this thing here. So query U, for example, in here is going to return which documents? U, 3, 5, 6, 7, and 8, right? Just look at the corresponding row. That's it, right? Okay, and these are your results. Now, not you is going to return. What are we returning for not you? Should be easy too, right? Anybody? 1, 2, 4, 9, and 10. Exactly. You look for the zeros. Everywhere there is a zero. Absolutely. So you take that line, you isolate it. So you can also take the complements, which is more indirect, but that's exactly the idea. Then we complement that, and then the ones tell us which documents these are. Okay. Now, U and Y. Can anybody tell me what U and Y returns? On Zoom, you can participate too, right? U and Y. Anybody? Yes? 5 and 8. Did you also want to say this? Who wanted to say 5 and 8? Great. Awesome. So this is it indeed. You take them, then you do what's called the bitwise AND, technically, if you go a bit in hardware, and then the result gives you the documents that contain both U and Y, right? So this is it. We can do it based on this construct. Now, U or Y, what would that return, U or Y? Anybody? Yes? Exactly. 3, 5, 6, 7, 8, and 10. Exactly. There's at least one of them that must have a 1. You can do it with a bitwise OR here, and then retrieve them. Absolutely. So now, just for the fun, doesn't matter if that's not immediate, but actually, mathematically, at least for the OR, it's not so simple for the AND or the NOT, but for the OR, you can actually view these matrices that contain Booleans as acting on what's called the module. You know the difference between a vector space and a module? So in a module, in a vector space, it's based on a field, right? But in a module, you do not require the inverses of the addition, right? So no, it's the inverse of the. I always keep missing this thing. So a module, you don't require the inverse of the multiplication, except for the 0 element. And in that case, if you see this Boolean set plus that's the OR and that's the AND, you can see the OR as a kind of addition, right? And the AND as a kind of multiplication, right? And then you have something that behaves a little bit like a ring, right? Where you have addition, multiplication, distributive, VT over them. And that gives you something that looks a little bit like a ring. And technically, when you have a ring instead of a field, then that's called a module instead of a vector space, right? But now to make it even worse, this is actually not a ring. It's not a ring because the addition, so the OR, doesn't have an inverse, right? So it's a semi-ring. So if you want to sound fancy in front of your friends, this is technically a module over the semi-ring Boolean OR and not and AND. And what you have, if you do that, that is absolutely beautiful, is that you can encode your query in here with a 1 for the terms that you're looking for. So we are looking for the second term and the fifth term. You put it as a row vector in here, and then it's a multiplication. You literally multiply these things, but you know the formula for multiplying, right? You sum over the coordinates and do the products of the pairs. You sum over the products. But here, the sum is an OR, and the product is an AND, and actually you recover exactly the results that you want, right? So this goes a little bit into the directions of LLMs that do it seriously with computations on numbers like that. But I just thought it's funny to actually abstract it in this way, that you realize that the particular case of OR can be executed by multiplying matrices, just accepting that it's not quite a vector space. Because again, it's not a field, it's a semi-ring, but you can still do matrix multiplication. All right, now I'm closing the parenthesis. It's absolutely no big deal if you forget that now. I just wanted to point that out, that we kind of see some linear algebra in there. All right. But now something I want you to be able to do is to give me the results of this query right here. Which query returns documents 3, 6, 7, and 10? One of these four. I don't know if I can display everything on my screen. I'll first display the first three. So I want results 3, 6, 7, and 10. Oh, I didn't start. Yes, that's true. It's because talking about semi-rings and modules actually already burned down my brain, so now I'm already slower. All right, so 3, 6, 7, and 10. So we have U or Y, we have U or not Y, we have U and Y, and we have U and not Y. U or Y, U or not Y, U and Y, U and not Y. All right, let's see what we have. We have a majority with U and not Y. So let's take a look. U and not Y. So we would have with just U 3, 5, 6, 7, and 8. Right? Oh, could I have made a mistake? I might have made a mistake. Okay. 3, 5, 6, 7, 9, and Y, which gives you the 5 and the 8. That's not the correct solution. That would be 5, 8. And not Y, you would have the zeros here that you look at together with the ones. So there would be 3. There would be 6, 1 and 0. There would be 7. And the 10 is my mistake. I just realized now that that should be 1 and 0 here. If we look at U or Y would give you 3, 5, 6, 7, 8, and 10. And U or not Y would give you 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it. Right? Who agrees? Just made a silly mistake with the 10. That's all. That's what you wanted to say? Yeah, absolutely. Just sorry about that. I just got the 10 wrong. I should have said 3, 6, and 7. Who agrees that U and not Y is 3, 6, and 7? Perfect. All right. But it was an opportunity to solve all 4 queries here. All right. So you see, I make mistakes too, which is to say that during all the learning, you can also make mistakes. That's totally fine. You can give wrong answers, and we are here to learn, right? It also shows I'm a human being, and I don't know everything. All right. Now, we were, I think, at 5, if I'm correct. We have 6 more minutes before the break. Okay, who is with me so far? Right? So we have these sets of terms, documents as set of terms. We have the matrices, and we are able to solve Boolean queries. All right. So now, before I get back to that and give you something even better than the matrices, I would like to just open a small parenthesis on something that we'll spend a whole week on, but it's the evaluation of a system. And that is something that you might have seen in machine learning, right? The type 1 errors, type 2 errors, false positives, false negatives. So we have them in here as well. But in order to understand why there can be false negatives and false positives, I need to tell you about information needs. Because if I tell you just out of the blue, there can be false positives and false negatives, you're going to be like, wait, that's just a Boolean operation, right? It's always correct. You just take the query, you compute it, you return the result. So it's always correct. There cannot be any false positive or false negatives, right? Who agrees with that, right? If I give you a query, the results are just correct. That's the computation. But the reason we might have some has to do with the fact that the query may not be exactly what you're looking for. Because there is a difference between what you're thinking in your brain, the research you want to conduct, and what your fingers are going to type on the keyboard. That's the reason why we might have false positives and false negatives. So imagine that we have this person who is writing her PhD on the impact of global warming on the development of butterfly ecosystems in southern parts of the canton of Uri between 2011 and 2013. So what kind of search might she write down as Boolean search? Maybe butterfly and climate and Uri and south, maybe Lepidoptera, which is a fancy name for butterflies and Ur and not winter, or central near Switzerland or Sweden, you never know. You know, some people might get that wrong, and not Luzern or Nidwald or Obwald or Stockholm and warmth, right? So you see there is an ambiguity. If I give you an information need, the information need would be what you have in the bubble in there. That is your intent. That's what you're looking for. And below is the query you write. Now, if you run a query like that, it might give you some results that technically are correct for the query, but that's not what you're looking for. So you might get false positives, documents that are irrelevant to you, or you might get false negatives, meaning that documents that you need, that you would like to see, but they are not returned to you because your query was not had not a wide enough scope to return these results. For whom is that clear? Right. So this is why we can have false negatives and false positives, because of this impedance mismatch between information need and query. All right. So now, in order to reason about these things, I'm looking at my results. So the results that I return are a subset of the set of documents, right? So the collection has all the documents, and I return a subset of that collection, some documents. Now, if I look closer, I will see that some documents, those in light green, are relevant to you. It means it matches the yellow bubble here. It's your information need. And the red documents, dark red, are irrelevant to you. They are in the results, but that's not interesting, right? So the query was not good enough. How can we measure that? And in fact, this is how we reason. We basically have the true positives that are the results that are returned and that are relevant to you. And we have the results that are returned but that are irrelevant to you. These are the false positives. And now we can compute something that's called the precision, where you just divide, it's a count divided by a count. You count the number of returned relevant results, the true positives, the number of documents in here, and you divide by the total number of documents returned, right? What is the precision of this here? Yes? 50%, exactly. 8 divided by 16, right? Who agrees? Right? So 50% means that half of what I got in the results wasn't relevant to me. A precision of, so this is 50%. What is the precision here, very quickly? 100%, exactly. Everything I got was relevant. Awesome, right? And here, what is the precision? 0%. All I got via my search results is just totally irrelevant to me, right? Probably I should have written my query in a better way. But now the precision is 0%, right? So you get how this actually works. And here, what's the precision? 80%, exactly. That is 80%. 8 divided by 8 plus 2. 8 divided by 10. Okay, you deserve the break. And after the break, I'll also show you the recall, and then I'll get back to a more efficient way of storing, which is called the standard inverted index after the break. Thank you.